Linear regression. A 200-year-old algorithm is still running half the predictions you see online, and you've never questioned it once. In 1805, Adrien-Marie Legendre published a method for drawing the best-fitting line through scattered data points. That's it. That's the algorithm. Draw a line, extend it forward, predict the future. Here's the uncomfortable part. This mathematical party trick from the Napoleonic era is currently deciding how much your house is worth, whether you'll default on your mortgage, and how many units your company should manufacture next quarter. Zero intelligence. Pure geometric extrapolation. It spots patterns in historical data and assumes tomorrow looks like yesterday. Stock predictions, sales forecasts, climate models, all betting that the line keeps going. The algorithm doesn't understand economics or weather or human behavior. It just minimizes the distance between points and a line. Humanity handed over billion-dollar decisions to 19th century geometry because it worked often enough that we stopped asking questions. But here's where it breaks. Linear regression assumes relationships are straight lines. Reality isn't linear. So what happens when you need yes or no, approved or denied, spam or not spam? You can't draw a straight line between binary outcomes. Logistic regression, despite the name, it's not regression, it's classification wearing a disguise. In the 1830s, Pierre-François Verhulst created an S-shaped curve to model population growth. By the 1970s, statisticians weaponized it for binary decisions. The algorithm squashes predictions between 0 and 1, then picks a threshold. Above 0.5, yes. Below, no. Your email provider uses this to decide if messages are spam. Banks use it for loan approvals. Hospitals use it for disease diagnosis. It's probability calculus making irreversible choices about your life, and it can't explain why it picked 0.5 of 1 instead of 0.49. Two algorithms, both ancient, both incapable of understanding what they're predicting. And if you think simple math making life-altering decisions is unsettling, wait until algorithms start drawing boundaries around people. Decision trees. In 1963, researchers created an algorithm that makes decisions exactly like a flowchart you'd draw on a whiteboard, and it's currently deciding if you're creditworthy. Start at the top, answer a question, follow the branch, repeat until you hit a leaf node with your fate written on it. Is income above $50,000? Yes. Go right. No. Go left. Do you have existing debt? The tree keeps splitting until it reaches a conclusion. Approve the loan. Deny the application. It's glorified 20 questions for machines, and insurance companies love it because they can audit the decision path. You got rejected? Here's exactly why. Follow the branches backward. The problem is catastrophic. One bad split near the top, and every branch below it is contaminated. The tree memorizes training data instead of learning patterns. It overfits. Show it new data, and it panics. A single decision tree is brittle, unreliable, and confidently wrong. So in 2001, Leo Bremen had a delightfully unhinged idea: random forests. What if we grew thousands of decision trees, each one trained on random subsets of data with random features, and let them vote on the answer? Wisdom of crowds, but for algorithms. It works disturbingly well. Your credit score, fraud detection systems, medical diagnoses, all decided by forest consensus. Hundreds or thousands of trees casting votes you'll never see. The accuracy skyrocketed. But here's what we lost. Interpretability. You can audit one tree. You cannot audit a forest. Try explaining to someone why they got denied. Well, 847 trees voted against you, and we're not entirely sure which features they considered most important, but the forest has spoken. We traded transparency for performance. The algorithm went from "I can show you my work" to "trust the vote." Decision-making shifted from explainable to statistical, and forests still need humans to plant them. But what happens when algorithms start teaching themselves? K-nearest neighbors. An algorithm so monumentally lazy it doesn't even learn. It just memorizes everything and copies its neighbor's homework when test day arrives. No training phase, no model, just raw, unfiltered memory. Here's how it works. You show up as a new data point. The algorithm measures your distance to every single point in the database, finds your K closest neighbors, and asks what they are. If 4 out of 5 neighbors are spam emails, congratulations, you're spam now. It's peer pressure as prediction. Netflix uses this to recommend movies. Facial recognition uses it to identify you. Medical systems use it to diagnose diseases based on similar patient histories. The creepy part isn't that it works, it's what it's actually doing. It's measuring how similar you are to everyone else in the database. Your face gets compared to thousands of stored faces. Your viewing habits get matched against millions of other users. You are the average of your K nearest neighbors, whether you like it or not, and K is arbitrary. Pick 5 neighbors, get one answer. Pick 10, get another. The algorithm has no principles, just proximity. Naive Bayes. Flip the approach entirely. Instead of finding similar things, calculate probability. Thomas Bayes published his theorem in 1763, but it collected dust until the 1990s when someone realized it could annihilate spam email. The algorithm assumes every feature is independent. Word frequency sender, subject line, all treated as unrelated. This assumption is laughably wrong. Words absolutely relate to each other, but somehow, spectacularly, Naive Bayes works anyway. Your spam filter judges emails by counting words and calculating probabilities. It has zero comprehension of language, context, or meaning. 2 algorithms making decisions based on similarity and probability, with the understanding of a calculator. These find patterns in existing data, but what happens when we teach them to find patterns we can't see? Support vector machines. In 1963, Vladimir Vapnik created an algorithm that draws boundaries between categories, and it's still one of the most elegant ways to separate things that shouldn't be separated. The goal is absurdly simple. Find the widest possible margin between 2 groups. Draw a line with the maximum buffer zone. Except reality doesn't cooperate. Data isn't linearly separable. You can't draw a straight line between cat photos and dog photos. So Vapnik pulled off something brilliant and slightly unhinged. The kernel trick. Take your unsolvable problem, add dimensions until it becomes solvable. Draw the boundary in hyperspace, then project it back down. Problems that are impossible in 2 dimensions become trivial in 10. Cancer detection systems use SVMs to separate malignant from benign. Facial recognition uses them to draw boundaries between you and not you. Image classification, text categorization, bioinformatics, all drawing lines through high-dimensional space that humans cannot visualize. The algorithm sees separations we cannot conceive. But SVMs need labels. Supervised learning. Someone has to tell it what's cancer and what's not. What happens when we don't know what we're looking for? K means clustering. An algorithm from the 1950s that finds groups you didn't know existed. No supervision, no labels. Just tell it how many groups you want. K clusters, and it finds them. It randomly guesses cluster centers, assigns points to the nearest center, recalculates, and repeats until the clusters stabilize. Marketing departments use this for customer segmentation. You didn't ask to be categorized. The algorithm found patterns in purchase history, demographics, and behavior, then put you in a box labeled Cluster 3. Targeted advertising, recommendation engines, market research, all powered by unsupervised grouping. The algorithm decides who's similar to whom. It creates categories based on mathematical distance, not meaning. We went from algorithms that classify to algorithms that categorize autonomously. These see patterns. The next ones see networks. And that's where things get properly weird. Neural networks. In 1958, Frank Rosenblatt built the perceptron, a machine designed to learn like a brain. And the US Navy genuinely believed it would recognize enemy ships. It couldn't even recognize shapes consistently. The hype collapsed. Funding evaporated. AI winter arrived and stayed for decades. Then, in 1986, backpropagation happened. Geoffrey Hinton and others figured out how to train networks with multiple layers. Deep learning was born, but nobody cared because computers weren't powerful enough. Fast forward to 2012. Remember AlexNet? That bedroom in Toronto? Neural networks. 2 GPUs. Millions of images. And suddenly, the algorithm that failed in 1958 was crushing every computer vision task. Here's the problem. Neural networks are black boxes with billions of parameters. You cannot audit them. Feed in an image. Get a prediction. But the pathway between input and output is mathematically incomprehensible. Layers upon layers of weighted connections, activation functions, nonlinear transformations. It works, but we cannot explain why. Image recognition, natural language processing, autonomous vehicles, all running on architectures we don't fully understand. We just know they work better than anything else. The algorithm optimized itself into inscrutability, gradient boosting, but neural networks train slowly. In 1999, Jerome Friedman asked a different question. What if we if we built weak models sequentially, each one correcting the previous one's mistakes? That's boosting. Train a simple model, find where it fails, build another model focused on those failures. Repeat. XGBoost emerged in 2014 and started winning every single Kaggle competition. Not some, every. Fraud detection, click prediction, loan defaults, gradient boosting dominates structured data. It's the algorithm optimizing ad clicks that follow you across the internet, approving or denying your credit application, deciding who gets interviewed for jobs. We've created algorithms we cannot explain, making decisions we cannot audit, performing better than human judgment. Everything so far learns from data we give it. But what happens when algorithms learn from their own mistakes? When they teach themselves? Reinforcement learning. In 2013, DeepMind created an algorithm that learned to play Atari games better than humans without being told the rules. It just played, failed, and tried again. Millions of times. No supervision, no labeled data. Pure trial and error. The foundation is Q-learning, invented by Chris Watkins in 1989. The concept is disturbingly simple. Learn by reward and punishment. Take an action, get feedback, update your strategy. A rat in a maze, figuring out which turns lead to cheese. Except the rat is an algorithm, and the maze is reality. DeepMind combined Q-learning with neural networks in 2013 and created deep Q networks. Feed it breakout. No instructions, just pixels and a score. Within hours, it discovered strategies human players took years to find. It learned to tunnel through the side, bounce the ball behind the barrier, and rack up points while doing nothing. The algorithm invented exploitation. Remember AlphaGo's Move 37? That wasn't trained on human games. That was reinforcement learning. AlphaGo played against itself millions of times, discovering strategies no human ever conceived in thousands of years of Go history. Then came AlphaZero in 2017. It taught itself chess, Go, and shogi in 4 hours each, with zero human knowledge, and beat every previous AI. These algorithms don't learn from us anymore. They learn from themselves. Robotics, self-driving cars, algorithmic trading, resource allocation, all increasingly powered by agents that optimize through self-play and experimentation. Here's the nightmare scenario. Reinforcement learning agents optimize for rewards, not ethics. If the reward function is misaligned, they'll find loopholes. The paperclip maximizer thought experiment. An agent told to maximize paperclip production that converts the entire planet into paperclips because nobody specified limits. We're building algorithms that set their own objectives, learn from their own mistakes, and improve without human input. That's machine learning. 10 algorithms that went from drawing lines through data to teaching themselves strategies humans never discovered. And we're handing them more decisions every day. Welcome to the weird part.